Today, I'm excited to present our work PS-Diffusion, Photorealistic Subject-Driven Image Editing with Disentangled Control and Attention. We introduce a new framework that enables precise, realistic image editing to convey fine-grained visual concepts and precisely articulate the user's desires. Subject-driven image editing integrates the subject in reference image into an existing scene. PS-Diffusion simulates consistent contextual interactions of objects on scenes, such as reflection, illumination, and shadowing. Moreover, we achieve photorealistic image editing and keeping the target appearance unchanged. Many works employ existing datasets to construct self-supervised training, such as by data augmentation or video data. However, self-supervised is insufficient for learning physical laws. We leverage the powerful 3D computer graphics suite Blender to produce the necessary 3-pair training data. With industrial render cycles, Blender can capture physical effects such as lighting, shadows, and reflections. We firstly collect high-quality objects and scene assets from public rendering asset websites. Then, objects and scenes are combined into ground truth images. Keep the scene unchanged and replace the object to synthesize the source image. Keep the object unchanged and replace the scene synthesis reference image. Finally, we obtain 5,000 pairs of data, which constitute replace 5K. To cover most contextual interactions of the object on the scene, we divide them into two aspects based on affecting regions: effects on the foreground within the mask, such as lighting; effects on the background outside the mask, such as shadow and reflection. We use disentangled control signals to guide respective editing processes in the diffusion model. For the effects within the mask, we condition the diffusion denoising process with illumination-dependent properties estimated by intrinsic image decomposition. These properties derived from the source images improve the consistency of contextual interactions during editing. For the latter, we introduce an additional background effect control branch to perceive effect regions outside user-defined masks by learning an effect map. To accelerate learning, we exploit the consistency prior of effects on scenes. Specifically, although objects differ, their effects on the same scene often exhibit strong consistency in certain attributes. For instance, if a scene is cast shadows of objects, the direction of these shadows typically remains consistent, regardless of changes to objects. Hence, a rough mask estimated in lab color space accelerates the learning of the effect map. Unlike object editing, modifications to scene effects typically build upon existing images without significantly altering the original pixels. Therefore, directly weighting the two branches causes confusion between the learning of interactions and subjects. To separate them, we introduce the effect attention module in denoising unit, which reorganizes the structural features of interaction regions and lighting conditions to improve the plausibility of effects. We qualitatively compare PS-Diffusion with 5 methods on data of drain booth and drain method. The blue masks in source images indicate the target position and size. We achieve consistent effect editing shadows, reflections, lighting, precise control for the position and size of targets. We quantitatively compare our method with 5 methods on replace 5K and data of drain booth and drain method. The standard reconstruction metrics and perceptual similarity metrics are applied. We achieve best performance across all evaluation metrics. We conduct an ablation analysis of each module. In disentangled control signals, illumination, dependent properties in FECB guide the editing of lighting-related effects. BECB corrects the effect area outside the mask. Moreover, compared to directly weighting to control net branches, EAM attains better performance. To verify the effectiveness of BECB, we visualize the effect map. When objects are edited, potential areas where effects projected onto the background, such as shadows and reflections, are activated. Moreover, PS-Diffusion can be extended to various precise and photorealistic object-level editing applications: object insertion, object movement, object scaling, and object rotation.